Let's place the current sheet in the XY plane with the current flowing in the Y direction with an amplitude of K sub Y amps per meter. We can visualize this current sheet as a series of wires that we lay side by side like this. And so forth. So now let's think in terms of looking at the edge of our current sheet. And so if we're looking at the edge, then the current is flowing into the page into the A sub Y direction like this. Let's focus on one of these current elements, this one right here. We know the form of the magnetic field intensity due to an infinite line of current. If you put the thumb of your right hand in the direction of the current, your right fingers will point in the direction of these circles of magnetic field intensity around this current filament. And we know that the magnitude of these magnetic field intensity lines is given by I over 2 pi times d, where d is the distance from the current filament to the magnetic field intensity line. We are now going to look at two current elements that are equal distance from the origin, say this one and this one. So here's our two selected wires on equal distance away from the origin, and let's look at the magnetic field intensity at this point on the z-axis due to these two currents. So for this current here, it would be this magnetic field intensity, and for this current here, it would be this magnetic field intensity. So looking at this point on the z-axis, the magnetic field intensity due to this current filament will be tangent to the circle, so this arrow will give its direction, and the length of the arrow will be the amplitude. And for this current filament, the magnetic field intensity will be represented by this tangent arrow, and again, the length of this arrow will be the magnitude of the magnetic field intensities. And so because the magnitudes are the same from the geometry, we can see that the result will be a magnetic field intensity just in the A sub x direction. Now, we can then use superposition and think about the magnetic field intensities due to this pair, then to this pair, then to this pair. And for each pair, we know the field is only in the A sub x direction, and when we add them up, going from 0 to infinity, we see the result is that we can only have a magnetic field intensity in the x direction. So the magnetic field intensity at that point will have some form of an amplitude in the A sub x direction. And this will be true at any point in space for z greater than 0. Because of the fact that this sheet is infinite in extent. Okay, now we can do the same thing below the plane, that is for z less than 0. So looking here, we see that the magnetic field intensity due to the current filament on the right would look like this, due to the current filament on the left would look like this, and the summation would be this. So for an equal distance below, we see that the magnetic field intensity at this point will have the same amplitude, h sub x, but it will now be in the minus a sub x direction. So now we're going to apply Ampere's circuit law that the integral of h dot dl around a closed path is equal to the current enclosed to determine the magnetic field intensity due to our infinite sheet of current. So let's take a path like this, where this top and bottom segment are parallel to our sheet of current, and the two sides are perpendicular. And let this point be minus L, and this point be plus L. So along the top segment, we know that the magnetic field intensity is constant, and it's in the A sub x direction. And that's also true for this bottom segment. It's constant and in the minus A sub x direction. And it will have the same amplitude because we will be equidistant. This line segment is the same distance below our current sheet. So this line segment here is the same distance below our current sheet as this line segment is above the current sheet. Okay, so let's find the integral of h dot dl. Okay, so we'll start, let's go along this surface here. So h is in the direction of our integration. So the integral of h dot dl from this point to this point will just be h sub x times 2l, our path length. Okay, as we integrate from here to here, we know along this segment h is in the a sub x direction, but d sub l is in the a sub z direction, so that dot product is 0, so the integral of h dot dl from here to here is 0. Now the integral from h dot dl from here to here, we have h in the same direction as our integration, so that integral also will be h sub x times 2l. And finally, when we close our path going from this point to this point, our integration is in the, or dl is in the a sub z direction, but our magnetic field intensity is in the a sub x direction, so that dot product is 0. Now this is going to equal the current enclosed, and that's the current going through this surface right here. So with your right hand in the direction of the integration, your thumb points into the page, so that's the direction of the current. So the current going into the page is the current density along here, which is K sub y, times this total distance, which is 2L. So we have 4LHX equals K sub y times 2L. So H sub x is equal to K sub y over 2. So looking back here, notice that it would not have mattered if we had taken, say, a path that was like this. As far as the result of the integration, we would have still obtained h sub x is equal to ky over 2. So in other words, the value of the magnetic field intensity is independent of how far away we are from our plane of current. So here's our final result, that when z is greater than 0, the magnetic field intensity is the value of that sheet current density in the y direction over 2, and the direction is in the a sub x direction. And when we're below the sheet of current, the magnetic field intensity has amplitude k sub y over 2, but now it's in the minus a sub x direction.